We're going to talk about parametric equations. We briefly mentioned this word before, but parametric is when we have something that is changing as a parameter. A parameter is a variable that we pretend we know the value of. Well, we're going to talk about representing the same curve in multiple ways. So a plane curve is what we're used to. We're used to a set of points described by an equation relating x and y. So this is an example of a plane curve, x plus y equals 2. So the set of values that make these equations true can be plotted, and they make a line on the xy plane. A parametric curve in 2 dimensions is a function whose input is a real number and whose output is a 2-dimensional coordinate. So you can think of this as taking in t plus 1 as an input, or sorry, t as an input, and outputting t plus 1 comma 1 minus t as the output. And it's kind of weird for our function to take in two values, sorry, take in one value and put out two, but that's what a parametric curve is really doing. It's taking in an input and outputting a coordinate as its output. It's possible to have one-dimensional parametric curves, but we're going to be mostly focusing on two-dimensional parametric curves. So the idea is that parametric equations are usually used to describe motion of objects over time. You've probably seen these in physics with x equals the starting position plus v times the initial x velocity, or the initial x velocity, and then times t, and y equals the initial y position plus the initial velocity in the y direction times t plus 1/2 times the acceleration in the y direction times t squared. And these ideas, essentially what's happening is as t changes, we get out an x coordinate and a y coordinate. So motion in 2 dimensions is really has 3 variables going on. It has the time, it has x, and it has y. So this is thinking about it as taking in time as the input and finding out what the x and y coordinates are at any particular time. To get a better sense of the difference between a plane curve and a parametric curve, think of this map. This is a set of points connecting New York and Boston, and this is what we would consider a plane curve. You can see all of the points, and this is what I think of as a plane curve. But if we have a parametric curve, it's kind of imagining, well, let's follow the path that it would take to get from Boston to New York. Well, that is a parametric curve, because this parametric curve is different from the parametric curve where you take forever to get out of Boston because of traffic, and then you go pretty quickly through and then slow down as you get closer and closer to New York. The speed at which you're going is considered in the parametric curve because it's not just telling you what path we're taking, but also how quickly we're going through each part of it. So if we wanted to evaluate a parametric equation, all we have to do is plug in the value of t, and we get x equals 4 times 5 squared minus 3 times 5, which is 100 minus 15, or 85. When we talk about these, we can talk about having other types of functions involved. This has an object following a parametric path with sine and cosine in it. So what we can do is we can plug in 0 here, and we get sine of 0. Sine of 0 is 0. So this is going to be 3 is our initial x coordinate. And then our initial y coordinate, when we plug in 0 for cosine, we get out 1. So this will be negative 7 plus 3, which is negative 4. Then plugging in 1 here, we get pi over 2. Sine of pi over 2 is 1. So we get 3 plus 1 is 4. Cosine of pi over 2 is 0. So we just get negative 7. 2, plugging that in, we get sine of pi, which is negative 1. So adding that to 3, we get 2. Putting in 2 in here, we get cosine of pi is 0. I'm sorry, cosine of sine of pi is 0. Cosine of pi is -1. So now we end up with -10. Plugging in 3, we get out -1. So there, it should be 2. Plugging in 3 here, we get out cosine of 3 pi over 2 is 0 times 3 is 0 minus 7, -7. So this gives you an idea that the object is starting at 3 comma -4. 1, 2, 3, 1, 2, 3, 4. It's going over to 4 comma -7. It's going down to 3 comma -10. It's going to 2 comma -7. So that's the path that the object has taken. Note that multiple parametric equations can have the same plane curve while representing different scenarios. This plane curve says, okay, let's plug in 0, and we get 0 comma 4. And then as we plug in larger values, we're going to be traveling along that line. So this line represents the parametric curve, where here's t equal to 0. But we could also talk about this parametric curve. If we plug in 0 here, we get -2 comma 0 as our starting point. And now when we plug in a larger value of t, it becomes more negative, and it actually is traveling the opposite direction along the line. So these are considered different parametric equations that have the same plane curve. This one is going up and to the right. This is going down and to the left. We've always talked about linear equations. Well, going up and to the right is the same as going down and to the left. Not true with a parametric equation. Just to give you a better sense of what parametric equations look like, here is an example of a parametric equation where you see here's a line that's been defined by a parametric equation, and by plugging in different values of t, I get out the point moving. Here you see this is a projectile motion where you have x changing linearly, y changing quadratically, and as we change t, you see it goes up, and then the value decreases. So this is an idea of the projectile. It's not always going to be, you can describe things that aren't functions with these as well. So here is an example of a path in 2 dimensions. And as we follow that path, it's described by parameters, but that it creates a sort of spiral. So we can use parametric, and you see the equation right there. So you can use parametric equations to create all sorts of curves that have directions.